It came without warning, a pulse of energy so powerful it briefly outshone everything in the Milky Way, combined. Satellites glitched, sensors fried. For a fraction of a second, Earth was bathed in radiation from a star we couldn't see. No explosion, no collapsing black hole, just a flash, and then silence. Scientists scrambled, astronomers checked their data twice. What they found wasn't a supernova, it wasn't a gamma-ray burst, it was something far stranger and far more dangerous. A magnetic monster spinning in the dark. A cosmic relic wrapped in invisible fury. They called it a magnetar. Not quite a neutron star, not quite a black hole. A thing so dense, a teaspoon of its matter would outweigh Mount Everest. But it wasn't the density that terrified us. It was the magnetism. A field so strong it could distort atoms, warp chemistry, twist the very fabric of reality. If one passed within a few hundred miles of Earth, it wouldn't collide with us. It would simply erase us. And yet, these objects exist, not in theory, in fact, in sky surveys and strange bursts and radio flickers from across the cosmos. But what are they? How can something so small be so violent? And why do they seem to appear, flare, and vanish? Tonight, we follow the trail, not just of the science, but of the suspicion, because the more we learn about magnetars, the more impossible they begin to sound. And that raises one final question. Are magnetars even real? Across the cold backdrop of deep space, there are mysteries too strange for science fiction. Somewhere far from Earth, a star once died. But it didn't fade into blackness. It didn't collapse into a singularity. Instead, it became something far rarer and infinitely more dangerous, a magnetic phantom pulsing with energy, hidden in silence. We didn't notice it at first. It gave no warning, no grand cosmic gesture, just a sudden, overwhelming burst of energy that sent shockwaves through the magnetosphere of our planet. It was December 27th, 2004, a date now etched into astrophysics history. A satellite hundreds of miles above Earth's surface was temporarily blinded. The Earth's ionosphere, typically a calm veil of charged particles, was rocked. All of it came from a single star. SGR 1806-20, they later called it. Located 50,000 light-years away, on the far side of our galaxy, in the constellation Sagittarius. To the naked eye, it's invisible. To telescopes tuned to gamma rays and X-rays, it is anything but. In a single tenth of a second, this object released more energy than the sun will emit in 100,000 years. And it did so not with fire, but with magnetism. The flash didn't just light up our skies, it challenged everything we thought we understood about the death of stars. This was no ordinary neutron star. It was something else. Something that could not only survive such catastrophic violence, but generate it. The term magnetar wasn't new. Theoretical physicists had been speculating about such objects since the 1990s, proposing that under rare conditions, a neutron star could form with a magnetic field so intense it would defy comprehension. But up until 2004, those ideas were just that, ideas. Theories trapped in equations, curiosities in chalk. Then reality broke the chalkboard. Magnetars, it turns out, are real. But what exactly makes them different? Why do some neutron stars quietly spin down into obscurity, while others become ticking bombs of magnetic violence? To answer that, we must understand their bones, their core, their origin story. Neutron stars are born in death. They're the compressed remains of supernova. Massive stars that exhausted their nuclear fuel, lost the battle against gravity and collapsed. The outer layers explode outward. The core collapses inward. At the edge of destruction, physics reveals something terrifying. The atomic structure of matter breaks down. In that instant, electrons are forced into protons, forming neutrons. The result is an object only about 20 kilometers across, but with the mass of an entire sun. It's unimaginably dense. One sugar cube of neutron star matter would weigh 1 billion tons. And yet Even among these monsters, some are stranger still. For reasons we still don't fully grasp, a small fraction of neutron stars, perhaps 1 in 1,000, are born spinning incredibly fast and with tangled, chaotic magnetic fields, fields that don't decay, fields that amplify. In their first few seconds of life, these newborn neutron stars undergo a magnetic detonation, a process we don't yet understand, but which might involve the rapid conversion of rotational energy into magnetic energy. The result is a magnetic field 1,000 trillion times stronger than Earth's. This isn't an exaggeration. That field is strong enough to destroy chemistry. If you were within 1,000 kilometers of a magnetar, the magnetic field would distort the electron clouds of your atoms, causing the very molecules in your body to snap apart. Not from heat, not from radiation, just from magnetic pressure. And yet, these stars are stable, at least for a while. They pulse in radio waves, blink in gamma rays, and sometimes unleash violent flares that can travel across galaxies. The mechanisms inside them remain hidden. We can't observe them directly, we can only watch what leaks out. For decades, we thought the most violent objects in the universe were black holes and supernovae. But then came SGR 1806-20. Then came other flare events. Then came the detection of fast radio bursts from magnetar-like sources. The universe had been hiding something far more volatile. And the question we must now ask isn't just how they work, it's why they exist at all. What physical law allows such concentrated chaos? How can a thing so extreme not tear itself apart? Are magnetars a freak accident, or a hint that we still don't fully understand matter, magnetism, and the true limits of stellar collapse? And more hauntingly, are they watching us even now, blinking in the dark, just waiting to erupt again? There are stars that shine, stars that burn, stars that explode, and then there are stars that whisper from beyond the grave. Magnetars don't belong on the usual list. They shouldn't exist, not according to the neat diagrams of stellar evolution found in textbooks or the well-behaved simulations run on Earth's fastest supercomputers, yet against all odds they do. To understand why, we have to rewind time, not just by decades or centuries, but by millions, back to when a giant was still alive. Massive stars are the engines of the cosmos. 10, 20, even 30 times the mass of our Sun, they live fast and die young. In their cores, nuclear fusion wages a constant war against gravity, generating outward pressure to balance the inward pull of their own immense mass. But this equilibrium is doomed. The star can't fuse elements forever. At first it fuses hydrogen into helium, then helium into carbon, and so on, each new element requiring more energy to produce than the last. But when it reaches iron, the game ends. Iron doesn't release energy when fused, it consumes it, and so the star collapses. Gravity wins. What happens next depends entirely on the mass and angular momentum left behind. For most massive stars, the core becomes a neutron star, an object held up not by conventional pressure, but by neutron degeneracy, the quantum resistance of matter to being squeezed any further. Anything beyond a certain mass threshold collapses past this state and vanishes behind an event horizon, becoming a black hole. But magnetars exist in between. Their mass is just shy of the tipping point, but their spin, their magnetic instability, off the charts. It's as if, in a rare cosmic twist, the star doesn't just die, it convulses. In that instant of collapse, when the core is compressed to a few miles across and spins hundreds of times per second, the magnetic field wraps around itself like a tangled coil. Theories suggest a dynamo effect may occur, converting rotational energy into magnetic strength, locking the newborn neutron star in a state of extreme magnetism from its very first moments. But here's the problem. The numbers don't work. The magnetic field strength observed in magnetars, over 10 to the 15th Gauss, should destabilize the very crust of the star. It should shear the surface. It should tear the object apart. And yet, they persist. It's not just strength, it's structure. The magnetic field of a magnetar isn't neat and symmetric like Earth's. It is twisted, contorted, braided into chaotic loops that lash and bend across the star's surface and beyond. And this chaos is not passive, it builds. Over time, stresses accumulate within the crust of the magnetar. The magnetic field lines shift, pressure mounts, and then sometimes something breaks. A magnetic loop snaps, a crustal plate shifts, and energy, trapped for centuries, is unleashed in a sudden, blinding flare. These events, gamma-ray flares, can be seen across the galaxy. They're not as bright as supernovae, but they carry more energy per square centimeter than almost anything else we've detected, and they happen in the span of milliseconds. But even this is not the strangest part. Magnetars fade. Some flare once and fall silent. Others repeat, but nearly all lose their magnetic intensity over time. The mechanism isn't well understood, but the decay is exponential. Within 10,000 years, a magnetar's field may weaken enough to render it indistinguishable from a conventional neutron star, and then it disappears into the galactic noise. This means that for all the ones we've seen, only a few dozen, there could be hundreds, even thousands we've missed. Dead, dormant, camouflaged among other neutron stars. How many of them are quietly spinning out their last magnetic whispers? How many lie near us, their power sleeping, waiting for some unseen instability to wake them once more? And what exactly is it that stops them from collapsing entirely? The boundary between a magnetar and a black hole is razor thin. Add just a bit more mass or push the neutron pressure just a bit further, and that field of magnetic chaos would vanish behind a veil of darkness. No signals, no bursts, just silence. Some scientists now wonder, could magnetars be temporary? Could they be stages rather than endpoints? Maybe a magnetar is just a brief phase, a scream in the dark before gravity claims the final word. Maybe some magnetars do collapse, but only after they've vented enough energy to make their mark. Others may never cross that line, content to burn out magnetically instead of gravitationally. And then there's another possibility, far more unnerving. What if magnetars don't represent an exception to stellar death? What if they represent a correction? A hidden stage in the life cycle of stars, one that only now, with our gamma-ray satellites and deep space radio telescopes, are we beginning to detect. A stage that rewrites what we thought we knew about how stars live and die. In the grand map of stellar evolution, black holes were thought to be the final word. But magnetars, they're a quiet rebellion, an anomaly, a reminder that nature doesn't follow our diagrams. And yet their very existence demands that we redraw them. Because if the universe can produce a star that burns with magnetism, that flares brighter than a galaxy, and that warps atomic structure without touching it, what else might it be hiding? To understand a magnetar, you must first understand its ancestor, the neutron star, not in name, but in essence, because what happens inside these stars is so foreign to our senses, so outside the world of atoms and elements and structure, that calling it a star almost feels dishonest. It is more like a fossil of physics itself. A neutron star is the aftermath of stellar death, a core so compressed that electrons and protons no longer exist as separate entities. Under the force of collapse, they are fused into neutrons, creating a massive ball of nuclear matter crammed into a sphere no wider than a city. It's like taking a mountain and compressing it into a marble, then compressing that marble again until gravity itself begs for equilibrium. In 1 teaspoon of neutron star material, you'd find more mass than Mount Everest. That's not poetry, that's physics. But it's not just the density that shocks, it's what it does to matter. At the surface, atoms are obliterated, nuclei are crushed together, electrons stripped and buried into the structure. There are no molecules, no chemistry, just a skin of degenerate matter, dense enough to stop almost anything from penetrating it. Beneath that crust lies the heart of the mystery. No one has seen the interior of a neutron star, but theories suggest it is layered like a cosmic onion. Only the layers are made of exotic states of matter we can't yet reproduce on Earth. Just below the crust, a superfluid ocean of neutrons flowing without friction, conducting heat with ghost-like efficiency. Deeper still, perhaps, a sea of hyperons, particles stranger than protons and neutrons containing heavier quarks, or even stranger. The core could be made of quark-gluon plasma, a phase of matter not seen since the first microseconds after the Big Bang. This isn't theoretical excess, it's necessity. At such densities, matter is forced into configurations we've only imagined. Normal atomic structure can't survive. Quantum mechanics takes over. And within this realm, where gravity, pressure, and quantum forces clash, magnetism is born. A neutron star already has a strong magnetic field, but sometimes it's not just strong, it's unstable. If the star is spinning fast enough at birth, its fluid interior can churn like a dynamo, amplifying magnetic fields far beyond normal thresholds. This isn't just the same mechanism that drives Earth's magnetic field, scaled up. It's a different beast entirely, one that may only operate under extreme conditions of density, spin, and asymmetry. If those conditions align, the neutron star becomes a magnetar. Inside this magnetic horror, the core could be a storm of particle interactions governed by laws we barely understand. Photons may convert into electron-positron pairs and back again. Magnetic pressure may rival or exceed gravitational pressure. Cracks may form in the crust as twisted field lines snap and reconnect. And all of this, every tremor, every flare, is hidden beneath a smooth, solid surface only 10 kilometers thick. A skin of iron and neutrons holding back a chaos that could level worlds. Even the space around a neutron star is no longer empty. Relativity tells us that extreme gravity warps time and space. Around a neutron star, this warping becomes intense. Time slows, light bends. A photon escaping the surface must fight against a gravity well so steep it loses energy, shifting toward red as it flees. A neutron star is the closest we can get to observing a black hole without falling into one. It's also one of the few places where our theories fail. Inside, the math breaks. Equations clash. General relativity and quantum mechanics, two pillars of physics, refuse to speak the same language. And that silence is deafening. Scientists have proposed ways to look deeper. Gravitational wave observations, pulsar timing arrays, X-ray polarimetry. Each new method is a tentative knock on a locked door, hoping the universe will let us peek through the keyhole. But magnetars aren't waiting. They speak in flares, in bursts, in brief, violent transmissions that suggest something is stirring inside. They're neutron stars pushed to the edge, not just in mass, but in magnetic intensity. Something has gone wrong inside them. Or maybe it's gone too right. Either way, a magnetar isn't just a neutron star with a stronger field. It's an entirely different kind of machine. And like any machine under strain, sometimes it breaks. In the seconds following a star's death, chaos reigns. The outer layers of a massive star are blown outward in a furious supernova, an explosion brighter than entire galaxies. But the real story begins inside. As the core collapses, gravity wins, and in that moment of compression, the ingredients for something far stranger than a neutron star are stirred into being. Because not all neutron stars are created equal. Sometimes the collapse isn't smooth. It's not a symmetrical, silent implosion. It's violent, turbulent, spinning. The stellar core, still retaining some of the parent star's angular momentum, begins to rotate rapidly, dozens or even hundreds of times per second, and this spin changes everything. Picture a dynamo, a spinning coil in a magnetic field generating electricity. Now multiply that by a billion. That's what's happening in these early moments of neutron star birth. Currents surge through ultra-dense fluids. Magnetic fields twist, tighten, loop around themselves like serpents in a jar. And then they snap. The birth of a magnetar may not just be a matter of high magnetic field strength. It may be a violent phase transition. As energy from rotation converts almost instantly into magnetic energy, the resulting field isn't merely strong, it's unstable. Imagine creating a magnetic field so intense that it fractures the very crust of the star that holds it. That's not theoretical, it's observed. In those first minutes, the newborn magnetar is blinding, not to human eyes, but to gamma-ray and X-ray telescopes. We call these objects soft gamma repeaters, or SGRS. They're light pulses in strange rhythms. Their bursts are erratic. Their energy output rivals that of supermassive black holes, even though they're barely 20 kilometers across. They are quite literally stars of pure magnetism. But why do only some neutron stars become magnetars? That remains an open question. It could be mass, or spin, or magnetic inheritance from the parent star. Some theorists suggest that if the progenitor star had a particularly strong magnetic field, that might seed the creation of a magnetar. Others believe it's a matter of symmetry breaking during collapse. If the explosion is off-center, just slightly lopsided, the internal currents in the collapsing core might twist differently, churning up chaotic field lines that fail to cancel each other out. Still others point to fallback accretion. After the initial supernova, some material may fall back onto the neutron star, spinning it up further and generating additional magnetic amplification. It's likely a combination of factors. But one thing is clear: once the threshold is crossed, there's no going back. The magnetar is born, and its fury begins. Its surface, barely solid, begins to crack under the strain. Starquakes, titanic fractures in the crust, rip through the body of the magnetar. Each quake releases enormous amounts of energy, triggering flares that travel for tens of thousands of light years, and we've seen them. On August 27, 1998, a flare from SGR 1900+14 lit up detectors across multiple space agencies. The pulse was so powerful, it temporarily ionized Earth's upper atmosphere. And yet, the magnetar was 20,000 light-years away. This is no ordinary behavior. This is cosmic-scale violence, without a visible explosion. The flares aren't from nuclear fusion. They're not jets like those from black holes. These are magnetic tantrums, field lines snapping and reconnecting, stress being released, a crust fighting to contain a force it was never built to hold. And inside? We still don't know. Some models suggest the core of a magnetar might be in a state of superconductivity, where magnetic fields can penetrate only in narrow, quantized tubes called fluxoids. As the star spins down and cools, those fluxoids migrate, twisting the outer field lines like a tangled slinky. When enough stress builds up, a quake erupts. It's a haunting image, a dead star shrieking through magnetism. There's another strange feature. Magnetars spin down much faster than regular pulsars. That is, their rotation slows more rapidly. Why? Because their magnetic fields act like giant brakes, emitting powerful electromagnetic radiation that drains angular momentum. In some cases, this braking is visible. A magnetar will slow its spin abruptly, an event called a glitch, as internal forces shift or rearrange. These glitches give us precious clues. They hint at layers beneath the crust, superfluid interiors, vortex pinning, and the behavior of quantum matter under extreme pressure. The kind of behavior that can't be replicated anywhere else in the universe, except perhaps moments after the Big Bang. What we're left with is an object so far beyond human intuition that it almost feels like myth. A neutron star, yes, but spinning too fast, with a magnetic field a quadrillion times stronger than Earth's, cracking under its own stress, fluctuating in brightness, screaming in radio waves and soft gamma bursts. A creature born from catastrophe, and yet, somehow, stable. For now. And that stability, temporary as it may be, is what terrifies scientists the most, because when it ends, the results aren't gradual. They are sudden, they are devastating, and they can happen again at any time. Across the cosmos, dozens of known magnetars pulse quietly, their fields coiled like springs. Hundreds more likely exist, undetected, blinking in and out of view. They might flare once in a century or lie dormant for 1,000 years. No one knows. But the next flare might already be on its way. At first glance, a magnetar is unassuming, just a spinning dot in a star chart, nothing but a blip in the vastness of the cosmos. But beneath that silence lies a force beyond comprehension, a magnetic grip so powerful it doesn't just attract or repel, it distorts. To understand how, we have to let go of what we think magnetism is. On Earth, magnetism is manageable. A fridge magnet, a compass needle. Even the Earth's magnetic field, powerful enough to deflect solar wind and guide migratory birds, is still just a whisper compared to what lurks inside a magnetar. There, magnetic fields reach 10 to the 15th Gauss. That's 1 trillion times stronger than a medical MRI. Strong enough to warp atoms. Not metaphorically, literally. Electrons are squeezed inward, reshaping the orbits of atoms into elongated needle-like distortions. The very geometry of chemistry bends. If you stood 1,000 kilometers away from a magnetar, your body would be torn apart, not by gravity, not by radiation, but by magnetic shear. The molecules in your cells would be yanked apart. The iron in your blood would feel an irresistible pull. The electrons in your atoms would stop behaving like they do on Earth. You wouldn't disintegrate. You'd unravel. The magnetar's field is so strong that even vacuum, the emptiness of space, starts to behave differently. In quantum electrodynamics, there's a prediction. In the presence of extremely intense magnetic fields, virtual particles flicker into semi-reality. The vacuum becomes polarized. Light itself bends. This bizarre effect is called vacuum birefringence. Normally, light travels in straight lines. But near a magnetar, light behaves more like it's moving through a crystal or a lens. It splits, polarizes, shifts. Observing this phenomenon is difficult, but there's growing evidence that magnetars are among the only objects in the universe where this quantum distortion of space can be seen. These aren't poetic metaphors. They're testable, observable consequences of field strengths that bend the laws of physics, and they raise new questions. Could such extreme environments tell us something about physics beyond the standard model? Could they be natural laboratories for string theory, quantum gravity, or dark matter interactions? Because if we want to understand where our current models fail, magnetars are likely where we'll see the cracks first. But it's not just what they are, it's what they do. Some magnetars emit fast radio bursts, millisecond pulses of radio waves so intense they've been detected from across the universe. For years, FRBs were a mystery. Then came the discovery of a repeating burst from a source matching a magnetar in our own galaxy. It was a eureka moment, but also a warning. These stars are capable of screaming across millions of light years with radio energy so loud it overpowers everything else in its path. And unlike black holes, which emit energy through matter accretion or relativistic jets, magnetars do this in silence. No surrounding disk, no nearby companion, just raw magnetic fury. In 2020, the Canadian Hydrogen Intensity Mapping Experiment, CHIME, recorded such a burst from SGR 1935 plus 2154, just 30,000 light-years away. It was the first FRB ever linked to a known magnetar. The burst was brief, but it proved magnetars can mimic phenomena from across the observable cosmos. Suddenly, a whole category of mysterious events had a face. But again, this only deepened the mystery. If these bursts are caused by magnetic reconnection events, akin to solar flares but vastly more powerful, then what kind of internal pressure must exist within the star to fuel such violence? And what happens when that pressure becomes unsustainable? The answer might lie in the giant flares, rare events where a magnetar emits more energy in 1/10 of a second than our sun will produce in 100,000 years. We've seen 3 of these in human history. One in 1979, one in 1998 and the unforgettable event in 2004. Each left a trail of disruption across space. Each demonstrated how close we are, even on the outskirts of the galaxy, to being affected by events light years away. Imagine for a moment if a similar flare came from a magnetar just 1,000 light-years distant, still well outside our solar system. The gamma radiation could strip away large portions of our atmosphere. Satellites would fail, power grids could collapse, life would endure, but it would feel like a cosmic near-death experience. That's not science fiction. That's physics. That's probability. Fortunately, known magnetars are rare. We've only positively identified around 30, but theoretical models suggest there should be hundreds, possibly thousands lurking in the Milky Way. Some are likely obscured by dust. Others may have quieted with age. But magnetism doesn't sleep. It decays, but it doesn't disappear. Even old magnetars long past their peak can flare, can twitch, can roar. And the terrifying thought is this: we might not know they exist until they announce themselves. A sudden radio burst, a flash in the X-ray spectrum, a glitch in a satellite, or maybe nothing at all. Just silence after the magnetic wave has passed. The power that warps reality doesn't need to be seen. It just needs to exist. It started with static, not the kind you hear between radio stations, but a whisper buried in the cosmic background, a flicker, a stutter, something that shouldn't have been there. Astronomers once dismissed these ghost signals as noise, equipment malfunctions, glitches in the feed. But the glitches kept returning. They had no fixed point. They didn't follow the rules of pulsars or quasars. They blinked, then vanished, milliseconds long, sometimes repeating, sometimes not. Too fast for stars, too sharp for galaxies. It took years to realize they were echoes, ripples, screams from a kind of star we barely understood, fast radio bursts, FRBS. They arrive like gunshots in the void, brief pulses of radio waves from far beyond our galaxy. Some last only 1,000th of a second, but in that sliver of time, they can carry as much energy as the sun emits in days. They are sudden, they are unpredictable, and they are, for the most part, unexplained. That is, until 2020. That year, astronomers caught an FRB from inside our own galaxy, SGR 1935 plus 2154, a magnetar, not a theory, not a guess, a real star pulsing out energy like a dying god clearing its throat. And for the first time, we had a suspect. But was it the only one? That question haunts every signal now, because FRBs don't follow a pattern. Some repeat, some don't. Some are wildly energetic, others are whisper quiet. They arrive from every direction. Some seem to come from galaxies with no stars bright enough to explain them. And yet magnetars fit the bill in a disturbing number of cases. Why would a neutron star, just 20 kilometers across, send out a signal strong enough to be detected billions of light years away? The answer may lie in magnetic reconnection, a sudden snap and reorganization of magnetic field lines, like solar flares on steroids. These events could generate shockwaves, driving intense emissions of electromagnetic energy across vast distances. But there's another possibility, one even stranger. What if the signal isn't caused by magnetism alone? Some physicists speculate that magnetars could interact with particles we haven't discovered yet, dark matter candidates, axions, or other exotic fields. If that's true, FRBs might not just be magnetic events. They could be hybrid phenomena, a collision between the known and the unknown. That would explain the irregularity, the randomness, the alienness of the bursts. It could also explain why some bursts seem to repeat in weird, uneven patterns, almost like a ticking clock but with skipped beats. That brings us to another eerie possibility. Magnetars may be the navigational lighthouses of the cosmos. Not for us, but for something else. Let's be clear. There is no hard evidence of extraterrestrial life encoded in FRBS. But some scientists have wondered aloud whether an intelligence could use magnetars as natural amplifiers, signposts in the void, chosen for their raw power and visibility. If you were trying to send a signal across billions of light years, why build a transmitter when the universe has already built one? Even if you remove the science fiction entirely, the fact remains. FRBs are a mystery magnetars may help solve, but not completely. There are still bursts that don't fit. Energies too high, locations too odd, repeaters that behave like nothing else we've ever seen. That means either there are many kinds of FRBs, or magnetars are capable of far more than we currently believe. And perhaps they evolve. Some magnetars appear to transition into other neutron star types. Others may slow down and retire, cooling and fading over millions of years into silence. But we've also seen stars we thought were quiet suddenly erupt. That suggests magnetars may sleep for eons, and then wake up in fits of violence. These echoes, these ghost signals, are like cosmic postcards from forgotten wars. We're hearing the aftermath, not the event. Because the light took so long to reach us, we're observing ancient history in real time. A supernova that happened before humans walked the Earth. A flare that lit up long-dead solar systems. A pulse from a spinning corpse that refuses to stay silent. And that silence is where the horror lies. Because if a magnetar went off close to us, closer than SGR 1806-20, we wouldn't have time to react. The burst would arrive before our satellites could warn us. The damage would be done in a blink, and we'd only understand it after the fact, if at all. That's the haunting irony. The most powerful signals in the cosmos are both warnings and relics, and most of them go unnoticed. Every time we point a radio telescope skyward, we might be catching the tail end of a cosmic scream, the death throes of a star warped by magnetic chaos, the result of physics playing dice with gravity and spin. The ghosts are talking. We're just beginning to listen. And if magnetars are the cause, it means something profound. That the most violent events in the universe aren't driven by gravity, but by something more subtle, more dangerous, a force that moves in silence, a field that distorts atoms, a ghost that echoes across time, a magnetic whisper hiding in plain sight. Every great cosmic event begins with a betrayal. A star, once stable, begins to falter. At its core, the delicate fusion that balances gravity's crushing pull begins to fade. Iron accumulates, inert and unburnable. The furnace that once turned hydrogen into helium, helium into carbon, and so on, down the chain of elements, finally meets its limit. And gravity, long held at bay, wins. What follows is not gentle. In less than a second, the core collapses inward at a quarter, the speed of light. Temperatures soar to hundreds of billions of degrees. Protons and electrons are crushed together to form neutrons. The outer layers rebound off the dense core in a supernova blast that outshines entire galaxies. It is one of the most violent things the universe can do, and it is not the end. It is the beginning. From this chaos is born a neutron star, a dense sphere of nuclear matter, barely 20 kilometers wide, spinning dozens or even hundreds of times per second. In that moment, a magnetic field is also born, one that carries the scars of the star's collapse. Twisted, amplified, and chaotic, it is a remnant of the star's former self, but stronger by factors beyond imagination. For most neutron stars, that magnetic field is immense, but manageable. For some, it is monstrous. And that's when we get a magnetar. How does one become the other? The precise recipe remains elusive. Not every neutron star becomes a magnetar. The conditions must be rare, perhaps requiring the parent star to be especially massive, spinning unusually fast, or possessing internal instabilities we can only guess at. But whatever the criteria, the result is staggering. A magnetic field 1,000 trillion times stronger than Earth's. It is not merely a product of the collapse, it is an exaggeration of it. A reminder that the universe does not always seek equilibrium. Sometimes it seeks extremes. This birth is not silent. The newborn magnetar wails in radiation. It emits powerful gamma rays. It glitches, suddenly speeding up or slowing down in ways we don't fully understand. These starquakes might be the cracking of its crust. Yes, a star can have a crust, under the strain of its own magnetic tension. Imagine a steel ball 20 kilometers wide with a magnetic field trying to tear it apart from the inside. Now imagine it spinning 30 times per second. That's not science fiction. That's real. That's happening somewhere in the galaxy right now. And if you could stand near it, not that you'd survive, you would see something terrifying, a dark, dead star pulsing faintly in X-rays, surrounded by a magnetic field so strong it warps the very vacuum of space. We believe that during their first 10,000 years, magnetars are most active. That might sound like a long time, but in stellar terms, it's a blink. After that, they begin to fade, cool and calm, at least on the surface. But under that surface? No one knows. They might remain restless for millions of years. Tension might build. And if something shifts, if the crust yields, if the field reconfigures, it can unleash a new burst of radiation strong enough to reach us across galaxies. That's what makes magnetars so haunting. They don't go quietly. Even in death they whisper, and sometimes they scream. Each flare tells a story, a release of pent-up energy stored since birth, a clue to the forces that shaped them, and a warning that this isn't over, that the universe still has cards it hasn't played. Magnetars are not the end state of stars. They are an intermission, a temporary phase that may lead elsewhere. Perhaps given enough mass and time, a magnetar could become something else entirely, like a black hole born from the continued collapse of a magnetic heart. But in that in-between stage they are unique, too dense to be planets, too small to be stars, too powerful to ignore. And in that uniqueness lies a larger truth.
The cosmos doesn't follow simple rules. It doesn't settle for neat categories. It creates edge cases, anomalies, objects that defy our checklists and redefine our limits.
Magnetars are one such object. They are born not to exist, but they do. They shouldn't be this stable, but they are. And in their strange existence, they teach us that the boundaries of physics are more like suggestions, rules the universe usually obeys until it doesn't. The fire that forged them has cooled, but its memory lingers encoded in magnetic fields we can't see, shaping stars we'll never visit, and reminding us that even in death, the cosmos has more to say. And so from collapse comes creation, from chaos, order, from death, a whisper of something new. And somewhere deep in that whisper, we are still listening. Magnetism, as we experience it on Earth, is gentle. It nudges compass needles, makes fridge magnets cling, powers motors and memories. But in the heart of a magnetar, magnetism becomes a weapon. It is no longer a background force, it is the main event. And to understand what this means, we must imagine what magnetism looks like when it is turned up to 11. And then kept going. A typical refrigerator magnet has a magnetic field strength of about 0.01 Tesla. A strong laboratory magnet, like the ones used in MRI machines, might reach 3 Tesla. The magnetic field of Earth is a humble 0.00005 Tesla. The surface of a sunspot hits around 0.3 Tesla. A magnetar? At its surface, the magnetic field can reach 10 to the power of 11 Tesla. That's 100 trillion times stronger than anything your body has ever encountered. That's strong enough to affect not just particles, but space itself. In this field, atoms are no longer atoms. Electrons are pulled into elongated shapes, orbiting their nuclei like flattened spirals instead of neat circles. Chemistry breaks down. Molecules can't form normally. The very rules of interaction that bind matter together are stretched and twisted. The field doesn't stop there. It reaches out, wrapping space in invisible tension. Near the surface of a magnetar, even the vacuum of space begins to behave strangely. Quantum electrodynamics predicts that in such extreme fields, virtual particles can flicker into actual existence. This is not hypothetical. It's a consequence of our best physical theories, a glimpse into a realm where the vacuum isn't empty but alive. This distortion of space by magnetism is called vacuum birefringence. Light itself changes when it passes near a magnetar. Its polarization shifts, its path bends, it slows. In a way, magnetars don't just warp matter, they warp the very medium through which information travels. To any nearby matter, asteroids, planets, even other stars, the consequences are devastating. If an object were to wander too close, it wouldn't need to be struck or pulled apart physically. The magnetar would simply erase its structure. Bond by bond, atom by atom, the invading matter would be dismantled, not from heat or gravity, but by magnetism alone. Imagine a planet's atmosphere being stripped away not by solar wind, but by magnetic pressure. Imagine metal liquefying without a rise in temperature. Imagine bones, electronics, molecules, all becoming unstable simply because they dared to exist too near. This is not just destructive, it is surgical, precise, efficient, and magnetars don't have to move to wield this power. Their fields travel, their effects ripple. Flares from magnetars, bursts of gamma and X-rays triggered by magnetic reconnection events or crustal shifts, can traverse space and affect other star systems. One such flare, as we've seen, hit Earth in 2004 and temporarily altered the ionosphere. That was from 50,000 light-years away. Now imagine one nearby. It doesn't have to crash into us. It doesn't need to throw rocks or sling radiation like a typical supernova. All it has to do is exist, close enough, and our atmosphere could be stripped, our biosphere disrupted, our satellites rendered blind. This makes magnetars, in a strange and terrifying way, the only known celestial objects that could potentially end life on Earth without ever making contact. And yet they don't. The nearest known magnetars are all safely tucked away in distant corners of the galaxy. Lucky for us. Or planned. Some physicists and philosophers have begun to wonder whether magnetars, by their very existence, might act as a kind of cosmic filter, a force of natural selection, not for life, but for civilizations. Think about it. If a highly magnetic event occurs near a budding civilization, a gamma burst, a flare, a starquake, their technology could be wiped out. Radio silence, global disruption. It would be the ultimate reset button. Not through violence or malice, but through pure, indifferent physics. This concept, call it the magnetar hypothesis, sits on the edge of science and speculation. But it asks an uncomfortable question. What if the universe has built-in hazards so extreme that only civilizations lucky enough to be born far from magnetars survive long enough to ask the big questions? And if that's true, we must count ourselves fortunate. Or are we just early? Could there be a magnetar lurking in the stellar nursery down the galactic street? Could its countdown already be ticking? Astronomers are watching, but the problem is visibility. Magnetars are hard to see unless they flare. Most of the time they're quiet, invisible in optical light, their true presence revealed only in X-rays, radio bursts, and the occasional terrifying outburst. It's not just science fiction. In 2020, the CHIME radio telescope detected an intense, millisecond duration fast radio burst from a known magnetar in our galaxy. It was the first time an FRB had been linked to a specific, confirmed object. The implication? Magnetars may be the source of many FRBs we've detected from deep space, signals so intense they were once considered possible alien beacons. Instead, they may be the screams of magnetic monsters, echoing across time. The mystery remains. How do magnetars store so much energy? How do they release it so suddenly? Why do some remain quiet for millennia, only to flare without warning? And perhaps more hauntingly, what would happen if we built our future, our satellites, our power grid, our data, and our lives only to have it all shattered by an invisible pulse from a star we can't see. Magnetism is not just a force. In a magnetar, it becomes something deeper. A threat, a puzzle, a message in a bottle hurled from the edge of physical law, and as we decode that message, we might begin to understand that magnetars aren't just remnants of death. They are reminders that the universe keeps secrets even in plain view. There are places in the universe where silence screams, where no light escapes, but sound, though not the kind we hear with ears, still finds a way to speak. Radio waves, invisible tremors, bursts that flicker for milliseconds and vanish into the abyss. This is how many of us first learned to listen for magnetars, not by watching, but by hearing their echoes. In the early 2000s, astronomers began noticing something peculiar. Brief, high-energy flashes in the radio spectrum, so fast they were often missed. These weren't the slow, repeating signals of pulsars or the rumble of solar storms. These were sharp, precise, and gone before a human blink. The phenomenon earned a fitting name: fast radio bursts, or FRBS. The mystery was immediate. Where were they coming from? Why so short, so intense? Were they natural or something else? Then in April 2020 it happened, FRB 242,028. Unlike the others before it, this one didn't come from billions of light years away. It came from within our own Milky Way, just 30,000 light years out. And it wasn't alone. It was accompanied by an X-ray burst, an unmistakable fingerprint. Astronomers pinpointed the source, a magnetar named SGR 1935+2-154. For the first time, a fast radio burst had a face, a name, a suspect. The implications were enormous. All those mysterious signals we'd been detecting from the deep universe, perhaps they weren't alien messages or exotic black hole collisions. Perhaps they were the howls of magnetars in distant galaxies, flaring and fading as they wrestled with their own magnetic madness. But how can a magnetic field create a radio wave? This is where magnetars blur the boundary between electromagnetism and extreme astrophysics. During a magnetic flare, the twisted, stressed field lines of a magnetar can suddenly snap and reconnect, a cosmic version of rubber bands stretched too far. The resulting explosion doesn't just release X-rays. It can jolt the magnetosphere around the star, creating oscillations, waves in the plasma, shaped and funneled by the magnetic field. Those oscillations can launch coherent bursts of radio energy, focused, fast, and unimaginably powerful. For a brief moment, a dying star becomes a cosmic broadcast tower. But these signals are more than just loud, they're precise. Some FRBs repeat, some come in structured patterns, some appear to echo in strange harmonics. It's no wonder that for years many researchers wondered if they might be artificial. But nature, it seems, can be far more clever. In some ways, magnetars act like haunted lighthouses. Their flares reach us across the dark, each pulse a scream from a star in torment. They don't flicker with rhythm like traditional pulsars. They burst, they vanish, they return when we least expect them. And sometimes they leave more than just sound. In rare cases, their flares can rattle nearby space so violently that gravitational waves may be produced, ripples in the very fabric of space-time. We haven't confirmed such an event from a magnetar yet, but the possibility hangs over us like static. And if they can send those waves, what else can they do? Could they trigger chain reactions in interstellar gas, spark star formation, or suppress it? Could the alignment of their magnetic fields with surrounding matter affect nearby physics in ways we haven't yet understood? One theory proposes that in certain dense stellar nurseries, magnetars might act as disruptors, bursting and sterilizing regions before planets can form. If true, magnetars don't just affect what is, they may prevent what could be. Which raises a haunting question. How many Earths were never born because a magnetar said no? Listening to the cosmos has become one of our most powerful tools. And now, thanks to observatories like CHIME in Canada and the Square Kilometre Array under construction in Australia and South Africa, we're hearing more and more of these bursts. The quiet void is suddenly alive with voices, ghosts in the radio, whispering of violent births and forgotten deaths. But even with better ears, we still lack eyes. Most magnetars are invisible in visible light. To truly see them, we must look with gamma-ray telescopes, with X-ray eyes, with instruments built to stare directly into the furnace of collapsed matter. Only then can we begin to trace their movements, their flare cycles, their lifespans, which it turns out are surprisingly short. Most magnetars burn fast and fade quickly. Within 10,000 to 100,000 years, a blink in cosmic time, their magnetic fields decay. They cool, their flares diminish. They become, in essence, silent neutron stars, still dense, still dangerous, but no longer loud. And yet, even then, they might not be done. Some studies suggest that magnetars could eventually collapse into black holes once they lose their outward pressure. Others believe they may retain strange properties, perhaps becoming exotic states of matter, like quark stars, if their cores continue to compress. So what are we really hearing in these radio ghosts? Are they death throes, birth cries, something in between? Perhaps each burst is a warning, a final shout into the darkness before silence falls. Or perhaps we're only hearing a fraction of the story, like tuning into one note of a symphony we barely comprehend. The deeper we listen, the more it becomes clear. The universe is not a quiet place. It is a place of sudden fury, of magnetic storms, of radio screams from distant skeletons of stars. And in this symphony, magnetars are the percussionists. They don't play often, but when they do, everyone listens. Imagine the surface of a world that isn't quite a surface. A place where the ground is not rock or soil, but compressed atomic nuclei, densely packed, crystalline, and locked under unimaginable pressure. Now imagine that this crust can break. Magnetars are defined by their fields, but it's their structure that allows those fields to act. Beneath their thin skin lies a battlefield of forces: magnetic stress, rotational inertia, nuclear pressure, and quantum rigidity, and sometimes that battlefield cracks. We call them starquakes. When a magnetar's crust fractures, the result is not subtle. These events can unleash flares that dwarf entire stellar outputs. The most powerful flares observed from magnetars, like the one from SGR 1806-20, are thought to originate from exactly this, the crust giving way under strain. But to understand how this happens, we need to go deeper into the exotic physics of neutron star interiors. At its core, a neutron star is a collapsed nucleus, a gigantic atomic structure where protons and electrons have fused into neutrons, creating a superfluid neutron-rich soup. But it isn't uniform. The outermost few kilometers are believed to be a solid lattice of nuclei suspended in a sea of electrons, a crust that behaves more like ultra-dense metal than any earthly surface. This crust is only about a kilometer thick, but it's immensely strong, perhaps the strongest material in the universe. Simulations suggest it could be 10 billion times stronger than steel, and yet it has limits. Over time, a magnetar's magnetic field becomes increasingly twisted. These fields aren't static, they evolve, tangle, and migrate. Differential rotation in the star's interior can stretch and stress the magnetic lines, generating forces that act directly on the crust. Imagine flexing a frozen steel cable over and over. It will eventually snap. When the stress exceeds the crust's yield strength, the lattice breaks. That rupture unleashes a jolt of energy, akin to a cosmic earthquake, that can shake the entire star. The tremor doesn't just release heat, it reorganizes the magnetic field, accelerating particles and triggering a burst of gamma rays or X-rays. These flares often begin with a sharp spike of high-energy radiation, followed by a longer tail of lower-energy emissions, sometimes lasting minutes. But even this extended glow doesn't tell the whole story. Hidden within the signal are quasi-periodic oscillations, ripples in the magnetar's body that act like seismic waves. By studying these oscillations, astrophysicists are attempting something extraordinary: neutron star seismology. Just as geologists learn about Earth's interior by analyzing earthquakes, astronomers hope to map the inside of neutron stars by examining their tremors. And what they're discovering is eerie. Some models suggest that the deeper you go, the stranger the matter becomes. The crust gives way to a nuclear pasta layer, where atomic nuclei stretch into spaghetti-like shapes under gravitational pressure. Beneath that, possibly a superfluid core of neutrons, and at the very center, perhaps even stranger things, free quarks, exotic particles, or states of matter we've never observed directly. Every crack on the surface may be a message from these alien depths, a momentary opening through which the interior of the star shouts into space. What's even more intriguing is that some magnetars seem to crack more frequently than others. This suggests differences in magnetic field strength, crustal composition, or even formation history. Some may have been born spinning faster, building more tension. Others might be the product of binary star interactions, magnetars formed in stellar collisions, or rapid mergers carrying the scars of chaotic births. This brings up the question, are magnetars evolving? Are their starquakes signs of aging or of something else, an inner instability reaching critical mass? And can these fractures be predictable? Right now, we can't forecast magnetar flares the way we can solar ones, but patterns are starting to emerge. Some stars show repeat behavior, quiet periods followed by flaring episodes, sometimes in cycles. If we can decode the rhythm, we may one day be able to listen for the next quake before it happens. It's not just an academic exercise. In April 2021, the magnetar SGR 1935 plus 2154 emitted another powerful burst. It wasn't as dramatic as the one in 2020, but it was accompanied by changes in its spin rate and emission profile. This suggests a deeper link between magnetic instability, starquakes, and the overall behavior of the star. In other words, these aren't just random events, they're symptoms of a larger system, a magnetic heart beating beneath a crust of cosmic steel. And if starquakes are the symptom, what's the disease? Some theorists propose that magnetars may be metastable, that is, balanced on the edge of collapse. Each quake could be a step toward breakdown. Over time, their crusts may weaken, their magnetic fields decay or tangle beyond repair. Their cores might compact further, leading to total collapse into a black hole. If true, we may one day witness such a death, the final scream of a magnetar as it collapses into silence. And what would that scream look like? It could be the brightest flare yet. It could be accompanied by gravitational waves or neutrino pulses. Or it could be strangely quiet, one last flicker before vanishing forever. For now, we can only wait. Watch, listen. Each burst from a magnetar is a reminder that even in the vacuum of space, even in the bones of dead stars, change is still happening. Pressure builds, tension mounts, and when it's too much to bear, the crust cracks and the cosmos shudders. We are fortunate Earth does not lie close to one of these ticking time bombs, because a nearby magnetar flare, especially one from a cracking crust, could be catastrophic. It could wipe satellites, strip atmospheres, blind sensors. Or worse, they are reminders of nature's quiet cruelty, of power wrapped in silence, of rage stored in atoms and unleashed without warning. In the universe, not everything dies peacefully. Sometimes it fractures. To understand a magnetar is to step into a storm, not one of wind or rain, but of warped space-time, violent fields, and energy so dense it reshapes the rules of physics. At the heart of every magnetar lies not just matter, but something closer to a malfunctioning engine of reality, spinning, surging, and collapsing inward all at once. And that storm doesn't stay contained. Magnetic fields don't simply wrap the star, they stretch outward, far beyond its crust, into vast magnetospheres that would dwarf entire planets. These regions are where the true chaos begins. A magnetar's magnetic field isn't just powerful, it's dynamic. As the internal field shifts, it twists the external lines into tight braids. These braids can store energy like wound springs. And just like a spring, the more it's twisted, the more violent its release when it snaps. This is what triggers the infamous magnetar flares. When the field can't hold any longer, it reconnects. An explosive process that accelerates charged particles to near light speed and floods space with gamma rays. These flares don't always come from starquakes alone. Sometimes the magnetosphere itself becomes unstable. It's like watching a solar flare, but 1,000,000 times stronger and infinitely more compact. But there's more going on here than just light. These reconnection events may also generate pair production, creating electron-positron plasmas right out of vacuum fluctuations. These antimatter particles briefly exist, annihilate, and unleash more energy in a chain reaction that propagates through the star's magnetic environment. It's an electrical storm in a vacuum, a war zone where magnetic topology is reshaped by violence. And remarkably, we can detect it. Magnetars emit not just gamma rays and X-rays, but also peculiar radio pulses. In 2020, astronomers linked a fast radio burst, FRB 200428, to a known magnetar. It was the first time such a connection had been made, offering a rare glimpse into these storms in action. Fast radio bursts had baffled scientists for over a decade, millisecond-long blips of radio energy from across the universe, often originating from no visible source. Now we had a clue. Some of them were storms from magnetars, beamed across galaxies like cosmic sirens. But what causes this precise flash of radio light? How can a magnetic reconnection, essentially a field reshuffling, create such narrowly timed, high-powered pulses? The answer may lie in the geometry of the magnetar's field itself. Like Earth, magnetars have magnetic poles, and their radiation isn't emitted evenly in all directions. Instead, it beams outward along curved field lines, often from the magnetic poles. If the star is rotating and its magnetic axis isn't aligned with its spin axis, much like a misaligned lighthouse beam, then the radiation sweeps across space. If Earth happens to lie in that path during one of these bursts, we see it as a quick spike of radio light, a blink, a glitch, a warning, and that opens another eerie possibility. If we're only detecting these bursts when the beam sweeps across us, how many more are happening unseen? How many magnetars are blinking in the dark, screaming sideways into the void, unnoticed only because we're not in their line of fire? It's possible, probable, that we've only seen a tiny fraction of the true number of magnetars in the universe. Their emissions are directional, their storms are brief, their signals faint and rare. For every one we've detected, there could be thousands more pulsing in silence. And while the majority lie far beyond our galaxy, the mere fact that one exists close enough to disrupt Earth's ionosphere, SGR 1806-20, reminds us that cosmic proximity is a matter of time, not distance. Because galaxies spin, stars move, orbits wobble. What feels safely distant today may not stay that way. Then there's the question of particle acceleration. In the heart of a magnetar storm, particles don't just swirl, they accelerate to such extremes that they enter quantum regimes. Curved magnetic fields can force electrons into tight spirals, emitting what's called synchrotron radiation, a signature of ultra-relativistic motion. And at the upper limits of energy, these electrons may even trigger quantum electrodynamic QED effects, situations where the vacuum of space behaves as a non-linear medium. Light no longer travels predictably. Photons scatter off other photons. The vacuum itself becomes polarized. This is no longer a storm. It's a breakdown of the classical universe. And yet, it remains stable. Somehow, this engine of destruction does not collapse under its own chaos. Magnetars persist. Their storms rage, but the stars remain, at least for now. Some scientists now believe that magnetars may play a key role in galactic evolution. Their magnetic winds could influence star formation. Their flares might seed complex molecules across vast distances. Their emissions may even help regulate the interstellar medium. In other words, these monsters might also be gardeners, from destruction, creation. It's a poetic inversion, and a reminder that in the universe violence often gives way to order. Just as supernovae scatter the elements of life, so too might magnetars shape the conditions for life to eventually arise. But there's another side to this storm. What happens after a flare? Some magnetars fall quiet for years as though exhausted. Others enter periods of repeat outbursts, like a storm season. Their spin rates can change, their pulses can vanish, then return. Some even seem to glitch, tiny, sudden changes in rotation that hint at deep internal shifts. This suggests that even the magnetic storm is only part of the puzzle. Beneath the field, beneath the crust, something else is moving, evolving, reacting. Each flare is not just an output of energy, it's a message from the interior, a Morse code from an alien world, trying to tell us what's happening inside. And maybe, just maybe, those messages are growing more urgent, because some magnetars appear to be aging fast, their fields are decaying, their emissions are changing, and according to some models, that could lead to a final phase. Not collapse, not supernova, but transformation, a state we've never seen, one that defies our models, a new kind of object. Because what happens when a magnetic field this intense begins to die? Does it simply fade? Or does it ignite something else, something deeper within the core? We don't know, but the storm continues. And we are watching. Death in the cosmos is rarely final. A star may explode, collapse, or fade, but its remnants persist, echoing across time. And so it is with magnetars. These magnetic monsters, born from stellar violence, do not simply vanish. Their afterlife may be stranger than their creation. But what exactly happens to a magnetar when it begins to decay? Unlike ordinary neutron stars, whose magnetic fields decay slowly over millions of years, magnetars burn through their power far more quickly. Their fields, wildly unstable from birth, begin to unwind and fade over just 10,000 to 100,000 years. In astronomical terms, that's a blink. And as the field decays, the star begins to change. The first thing to go is the flaring. Without the internal stresses and magnetic reconnection events, the violent outbursts that defined the magnetar's early life slow, then stop. Its crust, once buckling under pressure, stiffens. The storms calm, the radio pulses vanish. The magnetar becomes silent. But it doesn't go dark. Instead, many magnetars enter a phase where they resemble ordinary pulsars. They spin more slowly, emit low-level X-rays, and behave with a strange sort of mimicry, like a tiger pretending to be a house cat. Except under the surface, their history remains burned into their bones. Some astronomers have proposed that many of the dead neutron stars we've catalogued, quiet, slow-spinning, unremarkable, may in fact be extinct magnetars, their wild youth long gone, but with strange magnetic fossils still embedded in their cores. This raises an eerie thought. We may be surrounded by the corpses of forgotten giants drifting unseen. But what happens next? In theory, as the magnetic field continues to decay, the magnetar could become inert, a cold, slowly spinning ball of neutrons. But this is where speculation begins to stretch the fabric of physics. Some researchers have proposed that a decaying magnetar could enter a quark star phase, a hypothetical object denser than a neutron star, made not of neutrons, but of free-floating quarks. The transition could be triggered by pressure deep within the core once the magnetic field loses its stabilizing effect. If true, this would mean that some magnetars don't die at all. They transform, and what they become may defy our current understanding of matter. Quark stars, if they exist, would be so dense and strange that their surface would appear almost mirror-like, reflecting light in peculiar ways. They may have no crust at all, just a sea of quarks, bound by gravity, endlessly collapsing inward yet resisting the threshold of a black hole. We've never confirmed such an object. But some strange X-ray sources have behaved in ways that hint at something beyond neutron stars, and the death of a magnetar, particularly one with a decaying asymmetric core, might be the perfect factory. Then there's the final frontier: gravitational collapse. As magnetars lose their magnetic support, some may pass a critical threshold. Their spin slows, their energy leaks away, and one day they can no longer resist gravity's pull. They fall inward. The transition from a magnetar to a black hole would be cataclysmic. The last moment of emission might be invisible or blinding. A final silent implosion in the dark. And in that final instant, all the magnetic violence, all the gamma flares, all the strange quantum pulses, gone, swallowed, caged within an event horizon never to be seen again. But the story may not end there. Some physicists suggest that magnetars and their strange fates may leave gravitational echoes, not just in space but in space-time itself. The collapse of such a strongly magnetized, dense object may create ripples detectable by future observatories. In other words, magnetars might still speak, long after they're dead. There's another theory, one both unsettling and beautiful. It's called magnetar seeding. This idea suggests that the magnetic violence of a magnetar flare could seed nearby gas clouds with complex molecules. Carbon chains, organic precursors, even amino acids. These building blocks of life, scattered by flare winds, could become embedded in new planetary systems. Imagine that. A dying star hurling fragments of chemistry across space, not in fire, but in magnetism, not destruction, not silence, but legacy. This idea has sparked new debate about the role of extreme stars in astrobiology. Could life, as we know it, have been touched by the hand of a magnetar? Could some component of our own biology trace its origin to one of these invisible ghosts? We don't know, but the numbers are persuasive. With billions of galaxies and millions of potential magnetars, the odds of overlap are high. Somewhere, at some point, the remains of a magnetic flare may have fallen into a protoplanetary disk and altered it forever. And so, a thing that could kill from 1,000 miles away might also give life from 1,000 light years. That contradiction lies at the heart of magnetars. They are terrifying, beautiful, impossible, and yet real. As we peer deeper into the universe, building better instruments, launching telescopes into orbit, and tuning our ears to the static between the stars, we are hearing more from them. Bursts, pulses, glitches, events, and each one brings new questions. Why do some magnetars flare once and fall silent, while others enter cycles of repeat bursts? Why do some spin fast and others slow? Why do their magnetic fields persist for tens of thousands of years when physics suggests they should decay in hundreds? We're starting to realize that magnetars aren't just rare neutron stars. They may be something entirely different, a new class, a new stage, a hint that matter and energy, under enough pressure, behave in ways we've barely begun to understand. And that's the haunting part, because every mystery we unravel seems to point to deeper ones. Every detection brings more silence, more riddles, more impossible numbers. We've mapped hundreds of pulsars, dozens of black holes. We've catalogued exoplanets, cosmic microwave patterns, and dark matter candidates. But magnetars, they remain elusive, too faint, too strange, too fast, and yet somehow too loud to ignore. They are the sirens of the universe, calling across the void in broken pulses and gamma flashes, asking questions we still don't know how to answer. And as long as we listen, they'll keep calling. What if we've misunderstood them entirely? What if magnetars aren't just a footnote in stellar evolution, but a signpost, pointing towards something bigger, older, and weirder than we're ready to admit? Because the more we study them, the less they behave like typical astrophysical objects, and the more they resemble outliers, anomalies, glitches in the cosmic record. Some of the most controversial minds in physics have begun to float stranger ideas, not because they want to, but because the data refuses to behave. One such theory suggests that magnetars may not be entirely natural. The symmetry of their bursts, the precision of their flare intervals, and the peculiar uniformity of their field decay patterns have raised eyebrows. Some believe this might hint at an engineered structure, not artificial in the sci-fi sense of alien machinery, but designed by the laws of physics under exotic conditions we've yet to replicate. These so-called attractor theories propose that magnetars may be a natural endpoint of certain rare gravitational and quantum instabilities, that they aren't born randomly, but rather guided into existence by deeper laws we don't yet see, laws that operate beyond general relativity, beyond quantum chromodynamics. And if that's true, then magnetars could be revealing new physics in real time. Another hypothesis edges even closer to the speculative. The idea that magnetars are quantum testing grounds, cosmic laboratories that stretch the limits of known interactions. Within their cores, conditions exist that can't be recreated on Earth, not even in the most advanced particle colliders, the density, the magnetism, the crushing symmetry-breaking pressures. Some theorists suggest that strange matter or even preon states, hypothetical particles smaller than quarks, might stabilize within a magnetar's core. If that's true, then magnetars might not just be stars, they might be portals, not in the spatial sense, but in the physical sense, gateways to a different regime of matter, a state of the universe we don't currently inhabit, but that might have existed in the earliest instance after the Big Bang.
And perhaps a state it could return to.
Others go further still. There's a growing whisper in some circles about the possibility that magnetars are interdimensional ruptures, brief tears where brain theory or string fluctuations poke through into our observable reality, a magnetic echo from a higher dimensional event. These ideas for now remain unprovable. They hover at the edge of scientific respectability, not because they're inherently unscientific, but because the tools we need to test them haven't been built yet. But we've been here before. Black holes were once laughed out of conference halls, so were gravitational waves, so was dark energy. The history of astrophysics is littered with theories that began as blasphemy and ended as Nobel Prizes, and so magnetars persist. A cosmic itch we cannot scratch. Even mainstream researchers are now asking broader questions. Why do fast radio bursts, brief, powerful flashes of radio waves from deep space, sometimes appear to originate from magnetars? Are these bursts simply byproducts of crust quakes and field rearrangements? Or do they hint at something more coordinated? In 2020, a fast radio burst was detected within our own galaxy. That had never happened before. It wasn't coming from a distant source millions of light years away. It was local, and the culprit, a known magnetar, SGR 1935 plus 2154. The event was brief, just milliseconds, but powerful and eerily patterned. Some have speculated these bursts could be communication, not from intelligent life, but from the star itself, a kind of internal seismic scream released when magnetic stress builds to a breaking point. But even that raises questions. Why are the patterns so consistent? Why do they show clustering? Why do they sometimes repeat? We may be seeing a language of physics we haven't yet deciphered. One physicist described it like this. Imagine the Earth had no atmosphere, and one day you see lightning for the first time. No thunder, just a blinding flash. You have no idea what caused it. You don't know about clouds, charge buildup, or electrical potential. You'd see the lightning and think, that can't be natural. That's where we are with magnetars, the lightning before the thunder, a mystery in search of its theory. Then there's the unsettling idea that magnetars may evolve into something else entirely, that their decaying fields under precise conditions could trigger phase transitions in space-time itself. Theoretical models predict that if a magnetar's core crosses a certain density threshold, it might catalyze a false vacuum decay, an event where the local structure of the universe collapses into a more stable state. This sounds like science fiction. It's not. In quantum field theory, the universe we inhabit might be a metastable state, a kind of cosmic plateau. Under extreme conditions like those at the heart of a magnetar, that plateau could crumble. And if it does, the vacuum of reality itself would change. Light, matter, time, all rewritten. It wouldn't be an explosion. It would be a redefinition. So far, there is no evidence magnetars can trigger such events. But the math doesn't rule it out, and that's why some of the most cautious scientists treat magnetars not just with curiosity, but with fear. Not because they are malevolent, but because they might be the scalpel edge of deeper physics, operating just outside our grasp. And yet, for all the mystery, they remain beautiful, spinning, pulsing, shouting in magnetism across the void. Their very existence tells us that the universe is more violent, more intricate, and more poetic than we dared imagine. We used to look up at the stars and see only fire. Now we know better. Now we know that among those stars lurk dragons made of iron, cloaked in magnetism, burning with secrets, and perhaps watching us back. If magnetars are the punctuation marks of stellar death, then perhaps they are also clues, breadcrumbs left across the universe, pointing toward a hidden truth we've only just begun to read. Because behind the physics, behind the pulses and flares and incomprehensible fields, magnetars whisper something deeper, something more philosophical, something personal. They challenge our assumptions about what the universe is and what it's capable of. We were raised to believe the cosmos was stable, predictable, that stars live, burn, and die according to rules we more or less understand, that galaxies drift, that planets orbit, that chaos is rare. But magnetars are not rare. We now estimate that the Milky Way alone may contain thousands of them, most quiet, hidden, waiting. That realization forces a shift in perspective. The cosmos is not a calm place with occasional violence. It's a violent place that allows calm, temporarily. This reorientation runs deeper than science. It speaks to our place in the cosmic story. For every peaceful sunset on Earth, there's a star dying somewhere in silence. For every candlelit moment in human history, there's a pulse of energy flashing across space, unnoticed and unstoppable. We are small, that much is obvious. But magnetars show us we are not just small, we are fragile. Their mere presence in our galactic neighborhood is a reminder that we exist at the mercy of forces we don't control and may never fully comprehend. And yet, we are here. Alive, conscious, able to detect the flicker of a star 50,000 light-years away and ask, what is that? Magnetars are violent, but our awareness of them? That's miraculous. They tell us about the limits of matter. They hint at the birth of new physics. They tempt us with the prospect that the universe has chapters we've yet to turn to. But perhaps most importantly, they invite us to feel something we often avoid in science: awe. Not just at their strength, but at their improbability. At the idea that something so exotic, so alien, so utterly extreme exists. Not in theory, not in fiction, but in the fabric of reality. And awe matters. Because awe changes people, it forces humility, it invites curiosity, it sparks the next generation of questions. And sometimes, awe is the only appropriate response to something that exceeds language. Like a magnetic field that can twist atoms into ribbons. Like a dead star that can speak across space in gamma and X-rays. Like a cosmic whisper that says, you don't know everything, keep looking. So what do magnetars reveal about reality? They reveal that reality is not done surprising us. That the universe is not a finished puzzle, but a breathing organism with undiscovered organs. That the very laws we think are unshakable, relativity, electromagnetism, thermodynamics, may only be approximations, useful tools for now, waiting to be rewritten when we're ready. They reveal that nature doesn't care if something seems too extreme. If the math checks out, and sometimes even when it doesn't, reality will oblige. And they reveal that we, a species of carbon and curiosity, have the capacity to notice, to wonder, to reach. In that sense, magnetars are more than stars. They are symbols of the unknown, of the unfinished, of the unfathomable. And so the next time you look up at the night sky and see the soft twinkle of distant stars, remember, not everything up there is twinkling. Some are silent, hidden, waiting, wound tight with magnetic fury, pulsing in shadows just beyond the edge of what we can see. And maybe, just maybe, reminding us that even in the coldest corners of space, the universe is still writing new stories. Stories made of fire, stories made of iron, and stories sometimes made of magnetars. Are they real? Oh yes, and they are far from done with us. The story of magnetars isn't over. In fact, it's only just beginning. For all we've uncovered, the blinding flares, the eerie pulses, the unfathomable magnetic fields, we've barely scratched the surface. Each discovery leads to more questions. Each flare, a riddle. Each burst, a warning. And while the data we've gathered so far is breathtaking, it's also frustratingly sparse. That's because magnetars are elusive by nature. Their lives are short by cosmic standards. Their signals are unpredictable. And the ones we know about? They're mostly shrouded by dust, buried deep in galactic backwaters, or flickering in parts of the sky our instruments weren't watching. To truly understand them, we need new eyes, and those eyes are finally coming online. At the edge of the Chilean Andes, the Vera C. Rubin Observatory prepares to scan the entire sky every few nights, looking for transient events, short-lived cosmic flashes that flicker and fade. With its 3.2 gigapixel camera, it won't just take pretty pictures. It will capture motion, change, anomalies. And if a magnetar flares unexpectedly, the Rubin Observatory might be the first to spot it. Meanwhile, in orbit, instruments like NASA's NICER and ESA's Athena mission are poised to go deeper. NICER, perched on the International Space Station, is already gathering X-ray data with exquisite precision, helping us map out neutron stars in ways we never could before. Athena, when launched, will go even further, studying the hot, high-energy universe with sensitivity that could pierce the veil around magnetars and see what's really happening inside. But even these tools have limits. What magnetars require is coordination, a symphony of telescopes across Earth and space, watching in tandem, comparing notes in real time. That's where multi-messenger astronomy enters. When a magnetar flares, it doesn't just send out gamma rays, it may ripple space-time itself. It may send neutrinos screaming through the void. It may cause strange polarization effects in light we don't fully understand. The next step in magnetar research is to catch all of these messages at once, to listen not with one ear, but with many. Facilities like LIGO and VIRGO, designed to detect gravitational waves, are already being fine-tuned for the kinds of subtle signals a magnetar quake might emit. The IceCube Neutrino Observatory, buried in the Antarctic ice, is on the hunt for high-energy neutrinos that could point to a violent magnetar core collapse. And the upcoming Einstein Telescope, a next-generation gravitational wave observatory, could pick up the tiniest tremors from across the galaxy. Together, these instruments could offer our first full symphonic recording of a magnetar event. Light, gravity, magnetism, and neutrinos, all playing their part. But observation is only half the battle. The other half lies in theory, and the frontier there is just as wild. Computer simulations are evolving rapidly. Supercomputers can now model entire magnetar births in 3 dimensions, tracking the complex interplay between magnetic fields, nuclear matter, and the collapse of a stellar core. These models help us test hypotheses too dangerous or impossible to verify in real life. For instance, what happens if a magnetar's magnetic field twists so violently that its crust shatters like glass? What if that crustal quake triggers a gamma-ray burst? What if the field reconnects with itself, like tangled rubber bands snapping free? And perhaps most importantly, what are we missing? Some researchers think magnetars may be the key to unlocking the equation of state, a fundamental mystery that describes how matter behaves at nuclear densities. Others believe magnetars could be tied to quark matter, or exotic states of matter that exist only under extreme pressure. And still others wonder if magnetars might not be an end at all, but a transition, a phase in a star's life we don't yet fully understand. That's the thing about magnetars. They keep slipping through the cracks of our models. They're neither classical nor quantum. They don't behave like other stars. They don't even behave like other neutron stars. And their magnetic fields, those monstrous invisible arms, reach out in ways that hint at something deeper, stranger, more fundamental than we can explain. So what's next? Ambitious minds are already proposing dedicated magnetar observatories, spacecraft whose sole mission would be to orbit Earth and monitor known magnetars 24/7, waiting for the next pulse, the next flare, the next whisper from the dark. Others suggest deploying constellations of microsatellites, each tuned to a different frequency range, to triangulate events and pinpoint sources in real time. There's talk of quantum sensors, of new kinds of detectors that can measure minute changes in electromagnetic fields with unprecedented resolution. If these become reality, we might be able to see the magnetic field itself, not just its effects, but its shape, its spin, its evolution. And for those watching the sky with SETI-like intent, magnetars also raise the tantalizing possibility that some signals, some fast radio bursts, some unusual repeating pulses, might not be natural at all. We're not saying they're alien, but the very act of asking forces us to refine our tools, our theories, and our assumptions. Because the deeper we stare into the cosmos, the more it stares back, and sometimes it pulses with cold fury, with alien rhythm, with secrets encoded in magnetism and light. We stand at the edge of a new era, where the study of magnetars might not only teach us about stars, but about the very bones of reality itself, where every pulse is a puzzle, every flare a message, and every silence a dare to understand, a dare to observe, a dare to listen harder. Now we ask the final question: what do these magnetic titans truly reveal, not just about the universe, but about us? There are places in the universe that are beautiful, the gentle rings of Saturn, the graceful arcs of spiral galaxies, the delicate nebulae that drift like cosmic orchids across the void. Magnetars are not those places. Magnetars are brutal, chaotic, unforgiving. They do not shimmer. They burn. They do not whisper. They scream. And yet, in their violence, there is a strange kind of clarity, a moment where nature strips away its mask and shows us not its face, but its teeth. It's tempting to treat magnetars like anomalies, cosmic outliers, the rare mistakes of an otherwise orderly universe. But what if that's not true? What if they are the rule, and we're the exception? Think about it. Most of the cosmos is empty, cold, and hostile. Life, as far as we know, occupies a minuscule fraction of it. And for all our technology and telescopes, we have yet to find anything that even remotely resembles a sanctuary beyond Earth. But magnetars, they're out there. We know that now. We've seen them, heard them, felt their presence in the data. They live on timescales longer than empires, older than cities, more ancient than memory. And when they erupt, the entire galaxy flinches. So what are they really? Some say they're just neutron stars with extreme properties, a byproduct of stellar evolution, no different in kind than a nova or a black hole. That their magnetism is just physics dialed up to 11.
Others see something more mythic.
In ancient times, we spoke of gods with thunder in their hands, beings of fire and storm who could bend the skies and flatten mountains with a glance. It was metaphor, of course, allegory. But the universe, it turns out, has its own mythology. Magnetars are not divine, but they are profound. They are nature, turned inwards, compressed, concentrated, refined into something so potent, so precise, that it threatens the very scaffolding of our understanding. Because a magnetar isn't just magnetic, it's magnetism, made manifest. It's the raw force that holds atoms together, distilled into a single object, spinning, flaring, lashing out in pulses we barely comprehend.
And that begs the ultimate question: why? Why would nature create something so unstable, so lethal? What evolutionary purpose does a magnetic field so intense it rips molecules apart serve in the cold logic of the cosmos?
Unless it isn't evolution at all. Unless this isn't about purpose. It's about limits. Magnetars might not exist for a reason. They may simply exist at the boundary between matter and madness, between structure and chaos, between what physics allows and what it barely contains. In that way, they're like mirrors, not literal ones, of course, but conceptual. They reflect the edges of our ignorance, the places where math breaks down and models fail, the spaces where reality stops behaving the way it's supposed to and starts doing something else entirely. And the deeper we peer into those mirrors, the more we begin to see ourselves. Because we too are contradictions, matter wrapped in thought, atoms dreaming of meaning. We live on a planet held together by gravity, spinning through a vacuum lit by nuclear fireballs, protected by a magnetic field generated by molten iron. And most of us never think twice about it, but that same magnetism, the subtle shielding kind, has a monstrous sibling. A sibling that lives far away, and yet might one day reach out. If a magnetar erupted within 10 light-years of Earth, we'd likely never know what hit us. The gamma-ray flash would sterilize the planet's surface. The atmosphere would collapse, electronics would fry, and long before we had time to raise a shield or send a message, we'd be gone. Not because of war, or plague, or famine, but because a star blinked, and we were in the way. It's humbling, terrifying, necessary, because we live in a universe that is not designed for us. It simply permits us. And every so often it reminds us of that fact, not out of malice, just by being what it is. Magnetars don't care about Earth. They don't aim. They don't plan. But their very existence forces us to confront a brutal truth. We are temporary, our cities, our science, our species. But here's the strange comfort in that truth. So are they. Magnetars are born violently. They live briefly. They die quietly. Over tens of thousands of years, their fields decay, their flares fade, their pulses weaken. They slow, cool, and collapse into silence. Eventually, they become inert, invisible. Another dark speck drifting through space. In a way, they're like us, not in form, but in fate. Brief candles, brief monsters, brief gods. They shine, they rage, they end. And in the meantime, in the gap between flare and silence, we watch, we study, we try to understand. Because that's what we do. We, the observers. We, the stargazers. We, the strange little apes who dared to wonder what lay beyond the sky and found magnetars waiting there. And perhaps in doing so, we found something else too. Not answers, not yet. But a better question. Not just, are magnetars even real? But this: if reality includes something like magnetars, what else might it be hiding? Thank you for joining us on this extraordinary journey through the universe here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us each Friday at 7 p.m. Eastern, where we unravel the darkest mysteries of space.